All right, thank you for the introduction, and thank you for the invitation, Frank. So this talk will be my current view of what the gap is between automatic machine learning to automatic data science. So it's kind of me finally admitting to myself that I'm not really a machine learning researcher, but I'm more of a data scientist. And so I want to talk about a couple of the things that are very important to data science workflows that I don't think really get addressed in the machine learning community as much. And some of them maybe shouldn't be addressed in the machine learning or AutoML communities, but some of them I think the AutoML community is really set up well to address. And so I wanted to point that out and maybe encourage you to look into these issues more. So there's this cliche. This is from a Forbes article in 2016 that tells you that a data scientist spends 60% of their time cleaning and organizing data and only 4% refining algorithms. And I've seen a lot of talks that start with these statistics. Unfortunately, this is still the case. And I want to talk about what are the difficulties, what have we addressed, and what haven't we addressed. So I think if you take AutoML very strictly, then it's mostly the refining algorithms part, and that's really a very small part of what data scientists do. Also, this is only for building predictive models. Building predictive models is actually also just a part of what data scientists do, and arguably a rather small part. So motivated by sort of trying to look at a more holistic view, a couple of years ago I started this project called Tabular, data analysis baseline library, where I said, okay, let's look at a more holistic workflow. I'm including MLOps. This is all like Python library notebook kind of things. And so there's all these important steps: data cleaning, visualization, model building, evaluation, and so on. And usually you iterate a lot between those. And so I wanted to make this simpler and wanted to make iteration quicker. And so I built up a library to do a couple of these steps very easily so that I can iterate more often. And actually, I spent most of my time originally on the model building class, which the any classifier, which is sort of what is standard AutoML. And I took some inspiration from AutoScaler and some other libraries, and we built a portfolio and we tried to write some papers. And then I also included some stuff for plotting and type detection and explainability. And several years later, the most useful parts I found was for the cleaning, the type detection part, and the plotting. I've actually not used the AutoML in this, and I have not used really any other AutoML. Because as the slide before showed, well, actually the model building part is kind of easy. And probably, yeah, there's some really good AutoML these days, and it's probably going to be a little bit better than just doing a random forest. But usually the other factors are so much more important that actually the model building is not the most important part. So one of the things that I found really useful and that got incorporated into some other projects is the type detection. And this is something for which luckily we now actually have sort of a data set. I gave a link to the Sorting Hat paper here. So they collected hundreds of data sets trying to and annotated them for different types. And I built my own little heuristic. They used a machine learning approach in their paper, and there's pretty big disagreement between my heuristics and their machine learning, but it's not always clear what the right answer is. But I think it's actually great because there's a benchmark data set that we can work on, but I think it has gotten way too little attention so far. So detecting the types of data is actually quite difficult, and it's not even clear what the types should be. And it depends a little bit on the algorithms what types you want to detect. So there's not only categorical and continuous, there's also dates, but then also maybe there's free strings, but also there's things in between maybe. And then there's words thrown in, and maybe you don't know if an int is ordinal or not, or is it categorical or something else. And so that's actually kind of tricky to figure out. The other thing was plotting. So I find a lot of time as a data scientist is spent doing EDA. And so what I worked on was getting a plot in a single line of code. And so here, this is the Ames housing data set. It has like, I don't know, 100 columns or something. If you say plot and I want to predict this target, then it shows you some like cute plots. And that's actually the part of the library that people found most useful and were most interested in. And it's actually quite simple. And I'm doing some machine learning in the back, but it's mostly like univariate and bivariate statistics. But I think it's something that we could really try to tune. And that's really something that would be great to have. But no, I haven't really seen anyone in the Viz or ML communities working on this much. And there's no benchmarks, and there's not even a well-defined goodness metric. But it's something that would be really, really useful for data scientists. Oh yeah, so while I did this, there was also work called Lux by Dursley at the RISE lab, and she worked on more expressing different intents and then having visualizations for these intents. And whereas I worked more a little bit on like statistics to mine the data to find interesting things to visualize. So yeah, as I said, I think with AutoML, we've tried automating the easiest and fastest part of model creation. But as a data scientist, there's all the other parts of model creation. And then there's also things that are not model creation that are really important. And so I think there's three aspects of like what makes this work difficult and what creates this like 60% of data preparation. I think one of them is data discovery and system integration. It's known as master data management in the database community. I think it's a really important problem. It's probably not the problem that's most relevant for the AutoML community. There's actually some really interesting ML problems in discovery, and there's this, I put in a link here, you can see in the slides, to the system Kitana. They're doing AutoML, but they're spending most of their time trying to augment the data set with other data sets and see that it gives them a huge gain. And so I think related data discovery is something where machine learning can help. But I didn't really want to talk much about that today. What I want to talk more about is that a huge part of the work is in dealing with different kinds and shapes of data that the machine learning community, AutoML community doesn't really look at that as much. And also forcing things into classification regression problems when that's not really the problems that people are really interested in. I actually just had a conversation about outlier detection on time series. Outlier detection on time series is one of the most important problems in industry that every company has everywhere. And I don't think there's a paper on this on any of the last couple of Europes. It's like comparing like the importance of computer vision with outlier detection on time series data. It's very clear that outlier detection on time series data is magnitudes more important. But if you look at the machine learning research community, it's very different. So what I think our typical data scientist tasks are characterized in this way. So usually there's like, here's a data lake. Which means there's a bunch of servers with a bunch of different databases that are either relational or non-relational, and then maybe some text files thrown in, some images, and some other tables. And then, but I don't really know where all of them are. And then, okay, can you build and deploy a churn model for me? Okay, that's a relatively straightforward machine learning task. Getting from the lake to this task, or to a data set for this task, is already quite challenging. But actually, most commonly, the problems the data scientists get are like, oh, why did the sales for this product in this region drop? Or why is our website slow today? Like, what subpopulation is most at risk of mpox? These are the problems data scientists usually ask. And these are actually like statistical inference problems, but people don't address them with statistical inference. And OK, wait, is this my next? Yeah. And I'm going to talk more about these kinds of tasks in a little bit. But first, I want to start with the kinds of data that I think are most prevalent. And so first, I think most important data is tabular. And we saw this talk about foundational models earlier. And really, OK, obviously, foundational models are really important, particularly for text, for dialogue systems. But really, most important data is tabular. And there's no foundational model except for PFN for tabular data. If you had this medical applications, sure, you can read the whole medical report, and it's probably good if you can read it. But if you can read the 3 numbers that are the test results, these are probably the 3 most important numbers, and they're already formatted in a table. There's very specific things to the tables we see in machine learning. This is from the Lending Club data. And so one thing you can notice is it has 145 columns, so there's no way to actually look at it. But also, there's some things in this data that are really peculiar and very different from the assumptions in standard ML. In particular, one caveat in this one is it has a credit score, and it has an outcome whether credit was approved or not. And you're trying to do machine learning for whether the credit will be approved. How you're going to use the credit score depends a lot on whether it's this credit score before or after the approval happened. If you get because there's a causal relationship with between your credit score and getting a loan. If you get the loan, your credit score goes up. In this data set, it's not recorded when the time was the credit score is measured. And so the meaning is completely different if it was measured before or after you got the loan. And that's something that's kind of something that's very, very common. And so first I want to say, OK, tabular data is really important. But the other really important thing is that really all data is time series data in practice. Because data is usually collected in the real world, and the real world has this like 4th dimension that keeps going, and we can't really do anything about it. As an illustration for time series data, I have this great clock. I don't know if you noticed. This is in artwork in New York. It counts things. It's really hard to interpret. No one knows what it means, and it also changes what it means every once in a while. I thought this is, I think, a great representation of how timestamps are recorded. So there's, on the one hand, there's like timestamps in data that are sort of straightforward, but then there's also these implicit dependencies. Like I said, like when was a credit score measured? Or if you have the age of a patient in diagnosis, like was the age when the diagnosis was made, or is it the age now, or was the age when you first got the patient into the clinic? All of these have very different meanings. And we don't really talk about this in machine learning that much. In the database community, there's like things like time travel and as of features. So what was a feature at a given time? And it's actually quite important. The reason why these often can't really be disambiguated anymore is because data is not only always a time series data. It was actually also relational data, which means it was a bunch of tables that had different things like, oh, here's the patient data, here's when they arrived at the hospital, here's the medicine we gave them, and they're all recorded in different tables, and then someone made them all together into a single table to create a machine learning data set and put it in a CSV. That's also how someone created this loan data set, which is why it's no longer interpretable. And so really most data originally has like a multi-table form and then was flattened for ML. But really, OK, that's problematic because A, we lose some of the meaning. Also, the flattening is actually the feature important part. The feature engineering part. After you've flattened, all the feature engineering is kind of boring. All the feature engineering happens in going from the relational database, or most of the feature engineering, going from the relational database to a flat table. And it's actually quite non-trivial in many cases. Okay, so that was sort of the 3 things about the data. So basically, nearly all data is tabular, also time series and relational. And I think all of these are really understudied in the machine learning community, but also the AutoML community. The other part is, most of the time, we're not really doing predictive modeling. Because machine learning is very popular, people use predictive modeling for everything. But very often, the questions that we actually ask are inference questions. So the output is often not the typical thing, which is like a deployed machine learning model, but much more commonly, it's like a graph or a number or an insight. So what we really need to do, I think, is talk more to the business intelligence community, the statistics community, and the visualization community. And all of these communities have tried to get insight out of big data, is I guess what you call that. But they all come with different, very different backgrounds. And I think actually machine learning community is one that is very good with benchmarks. We have really, by now we have really good AutoML benchmarks, but for a lot of the tasks here, there's not really good benchmarks. Also, we're very good with automating things. So I think the AutoML community could really contribute a lot to these sort of visualization, EDA, and exploration tasks, which are most of the work. Also, both from being a professor and working in industry and working on scikit-learn, what I've seen over and over again, most questions that data science get asked are causal questions. And there's exactly 2 tools every data scientist uses for answering a causal question: a single scatter plot or the feature importances of a random forest. Neither of these is actually, and maybe you're using SHAP instead of the scikit-learn ones, neither of these is actually a causal inference tool. And I think as a machine learning community, the second one is a little bit our fault. So maybe we should also try to fix it a little bit and provide better tools. There's obviously causal modeling tools, but they're often hard to use, hard to understand. And I think that's something where the AutoML community could really help. Okay, so how are we going to do this? So I talked a little bit about all the things that I think are sort of kind of missing pieces, but I wanted to be a little bit more principled about okay, where should we start if we wanted to work on these problems? And I think one of the biggest things would be getting actual benchmarks that reflect real-world usage of machine learning better, or data science more general. I think we got better at having dirty tabular data, meaning I think there's now maybe 10 dirty tabular data machine learning data sets, which is probably not enough. But then there's things to do actual feature engineering, you can't really do feature engineering on most of these data sets. You think really you need relational data sets or time series data sets to do meaningful feature engineering. I'm not really aware of a lot of data sets for causal analysis, outlier detection, distributional drift based on deployed models. I haven't really talked about this much, but basically all problems become reinforcement learning problems once you deploy a model. And it's very hard to deal with this. And it's also something that basically every deployed model faces, but no one really talks about. Another thing that I thought would be really interesting, how about hypothesis creation? I think this is a great word. I think it was in one of the other keynotes. It's also an introduction to Hadley Wickham's book on data science. Is okay, there's hypothesis creation and hypothesis validation. And usually hypothesis validation is doing standard statistics, and hypothesis creation is looking at plots. And I think these are actually the 2 things that are kind of what most data scientists do most of the day. And we haven't really looked at either of them much. But I'm also not sure, what is a hypothesis creation benchmark, and can we make one? Because that's really the thing that is really like, what I try to do with Dabble, with the visualizations, is like someone gives me a CSV file, I'm like, what's in this CSV file? And they're like, and I do a plot and I get the result and I get some rough idea of what's happening. And it can maybe tell me, oh, there's this subpopulation that has this behavior, or these variables interact. But really having a benchmark to do this more in a more principled way would be something that I think would be hugely valuable. Okay, so at this point, I really wanted to talk about the work I've been doing after Dabble, which is like the Dabble version for relational data and with semantic annotations. But unfortunately, my boss's boss's boss said he wants to do this in his keynote in 2 weeks. So I need to wait for the announcement then. But something really great is going to come. But I can tell you why I think this is an interesting direction. I think getting closer to the source will make understanding data easier. You don't have to have as much type detection. You have more semantic information if you don't just have the flat table, but you have all the tables something comes from. And you might have additional metadata. And you might be able to really create rich features automatically. And so I can't tell you what I've been doing, but I can give you my competitive analysis, which are really interesting projects to work on. So all of these try to do AutoML to some degree on relational data, and using propositionalization, deep feature synthesis, or graph neural networks. And I think these are really cool directions. Also, these are mostly done inside startups. Some of them have like academic roots, but I feel like in the machine learning community, it's definitely like I would love to see more work on this relational learning. Okay, I'm going over a little bit because I started late. So just to summarize, I want more realistic data everywhere. Particular dirty tables, we've gotten some of them. More time dependent, meaning just time series, but also things that have like these implicit time dependencies, like features are measured at different times. Like in medical data, for example, you would have this like a lot. You have this in business data a lot. Like something happens at some point, and then you measure something else. Also, like the age of a user. If you record the age of a user in a database, obviously it's going to be wrong, right? But this is not something that we even think about in machine learning. And then obviously relational data. Okay, so maybe just a brief word about semantics. So what I mean by semantics is that often, if you come from business applications or really any applications, you often know more than just a floating point number. You might know this is a dollar amount. You might know this is a heart rate. And ideally, we want to make use of some of these things in our downstream models. So far, we don't even have a language to express this. So first, we need to express it, and then we need to understand how we can like use this in our modeling. Oh yeah, and the other thing is, I really would like to like broaden the scope of tasks and not just do like prediction. If we do prediction, at least like make sure you have interpretable models. Do things like root cause analysis, like why is this happening, is really the most common problem any data scientist ever gets asked. Thinking about causal models, doing decision support, and maybe even doing hypothesis generation, which is like, tell me what's going on with this data. These are, yeah, I think these are really, really common tasks, and I think there's a lot of aspects of these tasks that the AutoML community would be really well set up to contribute to, and yeah, I think that's it.
right, thank you very much for the wonderful talk. Are there any questions?
Yeah, thank you. Thomas, can you turn on the... Okay. Yeah, thank you very much for the talk. Very insightful. I'm wondering precisely about tasks like this, since we also talked in the morning a little bit about, well, LLMs, foundation models. There's a lot of stuff out there. People use code interpreter and stuff like that for tasks like this. It's really inefficient, but we don't have anything better. What should we do as an AutoML community merge with data scientists?
Yeah, I had a slide on this and I deleted it, and now I'm regretting it. But I mean, the thing is, the first thing is we need benchmarks, right? Before we can come up with solutions, we need to measure how good are the things that we're doing. And like, yes, you can use Code Interpreter and GPT-4 to generate plots, and we have no way to measure how good the plots are. So that's the first step. The second step, I think, is I think we should definitely use these tools. We don't want to use them on a row level. We want to ask them what tools to use. And so there's still the sort of low-level primitives like, can I go? Here. So there's some plots. And these like use some univariate bivariate statistics. And the LLM should be able to say, I want to do a scatter plot with the variables that have the most mutual information here and there. But you still need the tool to compute the mutual information, right? And you still need to have the heuristics to come up with good, like, building blocks. I don't think having LLMs generate matplotlib code is the right answer.
Thanks.
And maybe one more while the next speaker also sets up.
Okay, thanks for the nice talk. I was going to ask about the causal models. You hinted about using causal inference for such tasks. And I think one of the main barriers for causal models is actually formulating the cause-effect relationships. These, if I can say it informally, this information is embedded in the heads of the domain experts, but it's not easy to formulate these. Do you think this is a barrier for automating causal inference on such tasks?
It's causal inference with an unknown model, and that's just the problem that everybody's trying to solve every day, and they're using random forest feature importances for that. So you just cannot assume that you have the causal model. You can propose a causal model, and then maybe you can have an interactive feedback loop where someone says, no, this is wrong. I know the mechanism doesn't work like that. But I don't think you will get anyone to write down a causal model for you. You should assume it's unknown, and then you can have it validated. Also, yes, that's really hard.
All right, we're running a bit behind, so that'll be it for the questions. Please thank the speaker again with me.